Hi there. I will present our paper on the richness of calibration with Bob Williamson. So we consider the problem of evaluating probabilistic predictors. This is also relevant to fairness because probabilistic predictions are increasingly also made about people by algorithms. And for example, the risk of defaulting on a loan or for fraud detection. And the particular difficulty with probabilistic predictors is that we can't compare our predictions to some ground truth probability. It's not even clear whether there is such a thing as a ground truth probability. So I will assume a setting where we have data points which have some input features and some binary label and data points. And then we have a predictor p hat, which maps inputs to some probability between 0% and 100%. So a first idea how to evaluate probabilistic predictions could be to use some sort of frequentist reasoning where we have 100 data points for some input, and 60 of them are ones and 40 of them are zeros from the labels. And we could say 60% is a good probability for this. But the problem is that usually we don't have enough data. We don't have 100 data points for each possible input. So calibration is a way to go around this. Here we also take some groups, some subsets of the data set. And we might choose a similar data point in some way. I'll talk about this later. And then we can compute the calibration error of the group, which is the average prediction minus the average label. But yeah, how do we choose these groups? In general, we choose some groupings or a set of groups such that each data point is part of at least one group. And we use some notion of similarity. So one option would be to use similarity of predictions. This is often done. People use bins. So you look at the prediction space and say, okay, every data point with a prediction between 0% and 10% is in one group, then everything between 10% and 20% and so on. This is quite common. And an alternative that we look at in the paper is also when we use a partition of the input space. So we use we look at the features that we have, and for example, in the credit setting, and we then make groups based on the input features. For example, all black women earning between 50K and 70K a year in one group, then all white men earning between 40K and 50K, and so on. The advantage of the second approach is one that we can make sure that our groups are interpretable in a way that they're also connected in input space, because if we make this prediction space binning, then we might get very different people being assigned the same group because they have the same probability. And then we can't really interpret this group, and it's not clear that it has an ethical relevance as well. And the second advantage of input space partitions is that we can detect more forms of stereotyping. For example, if we have some relevant group, and there's, for example, in the credit case, there are people with very high income, very low income, and our predictor says 50% risk for everybody, although the higher earning people may have less risk of defaulting. And if we do this prediction space binning, then we still get all the 50% people in one group, and we can't detect this over and under prediction. But if we from the start say, okay, we look at the low income and high income people separately, then we can detect the 50% is over prediction in one group and under prediction in the other group. And obviously we can also combine both sorts of partitions. So we can do input partitions plus some binning. This is often done in multi-calibration, but there's a limit to how small our groups can get in order to get sensible calibration errors. And yeah, if we do this prediction space binning, then we can do less of the less fine input space partitions. And so there might be the situations where we want to have only one of the two. I'll skip the history of calibration. There's some insights that we talk about in the paper. Okay, then the second big part of calibration scores is about how do we get to population level scores from these group calibration errors. So assume that we decided on a grouping, and for each group we have some calibration error. Then a common way to aggregate this into a single score is by the expected calibration error. Here we assume that we did this prediction space bins, and then For each bin, we compute the calibration error, and then we take the weighted average of all of the bins of the calibration errors. And this gives us the expected calibration error. There's a variant, the maximum calibration error, where we take the maximum of the absolute calibration errors instead of the average. So these are two examples of how to aggregate. And we thought about, okay, what can we say more generally about sensible aggregation schemes? And we took an axiomatic approach and laid out some axioms which we thought are sensible for aggregation. And we know, then we draw on literature and from finance, where it's been shown that these axioms actually characterize the space of coherent risk measures. And within these risk measures, the mean and the max are the extreme cases and everything else in between, which shows us that the ECE and the MCE are in a way the extreme cases of sensible scores. And this also suggests that there are things in between that we can also use. This was about quality assessment of predictors, and we can also look at fairness more specifically, where there are basically two main differences, arguably. One being that we don't only want to look at the absolute calibration errors, because overprediction might be morally quite different from underprediction, because overprediction is usually of risk is usually bad for people, while underprediction might be good even for them. So we want to not only look at the absolute only positive errors, but also potentially negative ones. And the second big difference is we care more about the inequality between the calibration errors, not only the average or the maximum of these errors. And so we use different axioms, for this agglomeration. And these axioms characterize a set of deviation measures. Among them are the standard deviation and the maximum difference, which is already used sometimes in fair machine learning. And we also know that there's a close connection between these two spaces of agglomeration functions, which gives some further insights into these classes. I'll briefly go back to the grouping problem, because we so far only looked at partitions, input partitions or prediction space partitions. But we also suggest there's a different way to create groups, namely localized groups, which might be overlapping. So there might some data points can be part of multiple groups here. And the way to do this is, two ways that we investigate are k-nearest neighbor approaches and kernel methods. And for them, we can then create groups which are centered in a way around specific data points. So we can say we investigate we look at the calibration error around some specific point in input space. And we show that this gives us consistent estimators of the true calibration error if we assume that there's a true probability distribution, which is problematic, but it's often done and it's useful as a modeling assumption for proving the soundness of this approach, so to speak. And through these localized groups, we argue that there can get a individual notion of fairness, which is grounded in data as well. So to sum up, we look at many choices which are involved in measuring the calibration of a predictor. One big chunk is the grouping choices, in particular the principal. So whether we look at similarity of input space, similarity of prediction space, or also in some feature space, which we look at in the paper. Then I didn't talk here much about size, but also the grouping size obviously is a choice that we have to make. And then the grouping structure, where I mentioned the partition as one option, or localized groups which can be overlapping as another choice. And the second big question is how to agglomerate calibration errors which you have from the grouping. If we want to assess the quality, the general quality of a predictor, we might choose something between the mean and the max, some risk measure. And if we look at the fairness, we want to measure the inequality, and then we probably use some deviation measure. We argue in the paper that particularly in the fairness case, based on which structure we choose, we can look at either at group fairness notions or at individual fairness notions. But both of these assume that we have some representative data, because our calibration only works in relation to the data that we have. And it also doesn't tackle structural inequalities or other aspects of justice. So we see this as like one particular approach within the bigger project of just algorithms. Thanks for joining in.